I gotta admit, this is probably the biggest crowd I've ever bored with a machine learning talk. So I've been looking forward to this. Today is really about two main things, or two foci. One is hollows, and two is deep learning. And as far as I can tell, you guys already know everything about hollows, thanks to Valentina and Anna, who's talked this morning. I just wanted to make sure that we're all on the same page. So we'll just jump to my second slide. There you go. So just a quick rundown on what hollows are exactly in a nutshell. Hollows are geologically young depressions on the surface of Mercury, most likely associated with the loss of volatile species. You can see an example on the left, just those bluish, whitish features are the hollows we're interested in. And we do care about them because we care about them for many reasons, but the two most important ones are because they tell us about Mercury's volatile budget and volcanic evolution. Now, before we can answer those or address those relatively big scientific questions, we have to first understand where exactly the hollows are, how many there are, what they are exactly, what shapes they can have, and potentially also when they form, whether they form at all in present-day conditions. And this is exactly what has been done in the past. So with a couple of groups who looked at hollow distribution manually, so looking at mostly messenger images. And most completely that was achieved by Rebecca Thomas and others in 2014, who compiled catalog with about 445 hollow-bearing regions. Those are represented on the map below by yellow and green dots. And this figure actually comes from Dave Blewett and others' 2018 book chapter about hollows. And this is a great resource. So all we know about hollows is based on this foundational catalog. So that's really great. However, once you start zooming in on this, once you zoom in on those individual points on the map, you start seeing some issues. For example, the data is relatively coarse, spatially coarse, and doesn't represent the individual hollow scale. And that's visualized in this figure. You can see the white dot represents the data point in the catalog. But you see the hollows as white blobs all across the images, as indicated by the white arrows. And you can see that this white dot doesn't capture the small scale of the hollow. So you can imagine how we miss the geologic context, we miss the slope angle, we miss slope aspect, for example. So it's not just great at capturing that high level of detail. So what do we want? What do we need? There's basically three things we want. So in an ideal world, we would know every single hollow on the planet. We would know its exact geographic position, so longitude and latitude. And you would know or could derive a morphometric description. So we would know its area, shape, circumference, and orientation, for example. And that's visualized in the figure below. So you see, this is basically me drawing polygons around a couple of hollows. Ideally, you would just identify where they are and what shape and what form, what size they have, right? And just doing this for this little figure here took me about 10 minutes, right? And everybody who has done it before, who has used polygons to outline features on maps, for example, knows how tedious and slow that process is. So what we really wanted to achieve is to automate that procedure. And that's exactly where the machine learning or the deep learning comes in. So we built a deep learning tool, which we call the Hollow Retrieval Network, or HORNET in short, which is basically a convolutional neural network, or CNN, that's based on the YOLO version 5 architecture. And what it does more specifically is it does supervised instance segmentation. So supervised means, as you just heard, we create training labels, and instance segmentation means that we localize a feature in an image, we classify it, and then we draw a polygon around the feature or the target, which is the segmentation bit. And ideally, or ultimately, we want to train a model, we want to evaluate a model, and then deploy it on the entire messenger image data set, as is visualized below. Basically, have the model scan every single image one by one, outlining all the hollows that are in those images, as visualized by those white outlines in the center frame here. So that's the plan. But before we can even think about deploying this or a tool like this, we have to think about the training tool. And before we can do that, we have to think about the data. Right? Data is key. So I wanted to present the data set real quick. So this is focused entirely on the messenger narrow angle camera data set. There's about 112,000 images that we can use. The image properties of that data set are visualized in this figure. Just focus on the 6 large panels with the violet histogram. For example, in top left, we have in A, the image center longitude going all the way from 0 to 360, one full circle around the globe. In B, we have image center latitude going all the way from -90 to South Pole to +90° at the North Pole. We have in C, pixel scale going from something like 3 meters all the way to 150. In D, we have the emission angle, which is the viewing geometry of the image, 0 degrees looking downward vertically or nadir looking, and 90° would be looking parallel to the surface. In E, we have the incidence angle, which is basically the sun angle. So 0 would be the sun is overhead at local noon. There's no shadows. And then 90° would be the sun is right at the horizon, so very long shadows. And F, ultimately, we have the phase angle, which at 0° means the sun is behind you. And 180° means the sun would be in front of you. And you can see that the messenger dataset covers an extreme wide range of image properties. And that's horrible, actually, because usually we want your deep learning dataset to be very well defined and very well constrained. For example, you would want to have a very narrow pixel scale range. You would also want to have this similar emission angles, similar incidence angles, so your features, your targets always look the same, which helps your model learn how they look like, right? But in this case, we've taken the hard route because we have this wide field of properties. And there's one specific panel I wanted to highlight. This is panel B, this is the latitude. And you can clearly see that we lack images below 60 degrees south, right? They're completely gone. And I want to show this in the second figure. This is a map showing the entire surface from north to south. It's the equator in the middle. And you can see in the hex bins in the south are largely empty. So it's also something that you have to keep in mind when you use deep learning. You will always be limited by the data set that you're using. And in this particular case, we're just blind in the south, right? It's just how it is. But it's important to acknowledge that, of course. There's something else that's important about the data. As we want to develop a tool that is able to ultimately scan through the entire data set, we of course have to use a training and evaluation data set that is representative of the full scale data set, right? And this is shown by the small boxes, the small panels with the black histograms. This shows distribution of properties in our training and testing data sets. So you have to try to closely match the distribution of properties between the training and testing and your full data set, of course. Otherwise, your model wouldn't be able to detect hollows in all those images, right? And you can see that works pretty well, but not always perfectly well. And it's also, of course, limited by the fact that not every image that we could draw from the overall data set has a hollow in it, right? So you're also limited by the knowledge you have before you deploy the tool on the global scale. And I wanted to highlight the importance of the data just one more time by looking at something that I like to call end members. It's just extreme cases of the data set. In this particular case, I would like to focus on the pixel scale, the emission angle, and the incidence angle. And that's showcased here. You can see on the left, this is pixel scale. At the top, we have a very high resolution. This is about 3 meters. At the bottom, you see a low-res image, about 145 meters resolution. And you can see that in the top image, hollows are clearly visible. It's a beautiful image. At the bottom, you see that hollows are reduced to a couple pixels, a couple dots on the surface. And again, I have to underline that our model has to be able to detect hollows in both those frames. And then in the center, you see the same for emission angles, a very low emission angle at the top and a very high emission angle at the bottom. And you can see how circular craters become very elongated in high emission angles, right? And of course, our model has to understand that as well. And then on the far right, we see incidence angle on the top, a low incidence angle, no shadows. The reflectance of the surface is dominated by albedo. So we see how the hollows appear all in their glorious brightness. And at the bottom, very high incidence angle, 85 degrees, long shadows, and we barely see hollows anymore. So our model has to be able to deal with all of that. But luckily, there's a couple of ways how we can achieve that besides being smart about how we pick our training data set. We can also use something called data augmentation. That's common practice in computer vision. It's basically describing the process of modifying your images in a certain way. You can rotate images, you can flip them up, down, left, right. You can modify the contrast, the brightness. You can warp them, you can shear them, translate them, all kinds of stuff that you can do. And this is just visualizing those examples here. In the first example at the top, we see rotation, we see 2 flips, up, down, left, right. We see a change in brightness and contrast. And that's great, for example, to mimic different ranges of solar azimuth angles, because you can rotate the shadows basically. At the bottom, we see another example where we do also warping, like squeezing the image together basically. And that enables us to mimic emission angles, for example. So that's really useful. Of course, as you certainly can imagine, we have to be careful with our augmentation. We can't go entirely wild, because there might be environmental or physical constraints to how our target can look like. So augmentation must always reflect the reality. So this example is actually from Mars. This is a dust devil on Mars, taken or acquired by the MRO high-res camera on MRO. And as some of you might know, MRO is on a sun-synchronous orbit, which means that it revisits the same spot on the surface roughly the same local time. It's about 3 p.m. in the afternoon. And that means whenever you're using map projected images on Mars, map projected high-res images, that means that the sun will always be in the west. So a dust devil will always cast a shadow to the east, right? So when I augment this data set for training purposes, I can easily do up-down flips. That should work. But I shouldn't do any left-right flips, because then the shadow is on the wrong side of the target. And that actually makes it harder for the model to learn what it's supposed to learn, right? So you always want to be smart about how you augment your data, full control over what you're doing with your augmentation. Okay, once you have that handy and we can actually deploy our model, this will end up hopefully produce something like this. So this is the final version of Hornet, fully trained. It will produce outputs like this. So you see on the left is a low incidence angle example, a couple of hollows outlined with boxes and polygons. And on the right, a high incidence case where the model is still able to detect the hollows and outline them with polygons. So that's very promising. This looks great, right? But we always have to remind ourselves that deep learning outputs will never be perfect, obviously. There will always be small and large mistakes. For example, on the left, you can see that some of the hollows are detected multiple times. So that happens all the time. And also be aware that once you actually scale up your model from your local training and testing scale to the global data set, there's always something that's going to be off, right? Speaking from experience over the past 8 years on bodies across the inner solar system, there's always something you didn't anticipate. So always be on the lookout. And that's also why I would always recommend that you actually review the data once it's produced by your model, if you can. So in this case, for the Hornet case, for example, we looked at every single detection. You can do this with a dedicated Python script. You could just bring up the source image. You could plot the detection on your image, and then assess that with your colleagues in tandem or something like that. And that sounds tedious, but actually just once you get used to it, it's just a fraction of a second that you need to actually go through one candidate, and you can blast through tens of thousands of detections real quick. It's a couple of hours basically. But it really helps you to kick out all the bad detections. And that, of course, helps to build trust in the data set at the end. So in the Hornet case, on the right, you see a couple of false detections that Hornet likes to make. It very much likes small, bright craters. It also likes fields of secondary craters. And for some reason, it also very much likes cosmic rays, so in panel E, which is something I would never have anticipated before I deployed the model on the global scale, right? Just, of course, want to acknowledge the fact that sometimes your data might be so big, if you're mapping craters or boulders, for example, you will see tens of millions of features. You wouldn't be able to review those anymore, of course, but always be mindful of the limitations of your results. All right, so this is the product. So after all these steps, after all these efforts, we finally get our global product. So we scanned every single messenger image, about 112,000 of them. It took the model less than 60 seconds to do that. So it's really, really fast. That's probably the best selling point of deep learning, really. It's really fast and produces very nice global catalog of hollow locations. And this is all reviewed by me and my co-authors. So every cross on the map is one verified hollow detection on the surface. And you can see there are a couple of regions that have a higher density of hollows. Those are highlighted by the heat map in the background. So yellow colors indicate high densities. And of course, you have an elevation map in the background. And what I wanted to highlight here is that we identified 19,000 individual hollows so far. But if you actually do the math and try to understand or consider how many images we are, or how many spots on the surface we are still missing with images and coverage, and include this with or combine this with the performance of the tool, we estimate there might be up to 170,000 hollows on Mercury, actually. So it's a very big number of hollows. It's far more than just 400 than we knew about before. Okay, and I don't have time to go into any scientific details. I apologize, but just wanted to show a little teaser here. So once you have the global data set, we can finally do some science. This is what we care about, actually. So we can do spatial distributions. We can look at size frequency distributions. And things we found, for example, in the data set is that we clearly see that the size of hollows increases the closer you get to hot poles. And for example, on equator-facing slopes, so this indicates that temperature is very important in controlling the growth of hollows. We also see that hollows, or that more hollows are located in regions that see or experience more or higher rates of micrometeorite impacts, right? So a couple of things that we discovered in there that are really interesting that I can't talk about now, but if you're interested in that, I would highly recommend checking out those papers. So this is the reference right there. It's being paid for, it's proved, so it should come out any second now. So I hope this will appear soon. And of course, the data is also available. You can easily use the code here, or screenshot it, whatever, or click on the link, or type in the link. And of course, I wanted to highlight there's a companion paper coming out as well, led by Ariel Deutsch, who's using the data set to focus on hollow degradation stages. Okay, I wanted to close with this slide. It's just the three main takeaways that I wanted to communicate today. A is that deep learning is really a fantastic tool to lift the geostatistical and morphometric analysis of all kinds of features to a whole new level, right? It opens a couple of doors, right? But at the same time, it is not a magic tool that is expected to solve all of your problems instantly. So, and a side note, Hornet brought us from 400 hollows all the way to 19,000. Is the data set perfect? No, it's obviously not perfect, but it's still quite a big leap forward. And the second point that I want to communicate is that planetary deep learning is strongly controlled by the data. So dataset awareness is key, it's absolute key. And augmentation can help you to address the data issues, can help you to address label scarcity, but only if you do it properly. And always think about environmental and physical properties that might help your model or impede your model learn certain targets and backgrounds. And then C, last but not least, deep learning should never be and will never be a replacement of human expertise, of human brains. It is really, think about it as another tool in your toolbox. It's not the solution to everything, it's just another tool in your toolbox, really. And deep learning models will always miss targets, they will always make mistakes. So review data sets if you can, and if you cannot, always view results in the context of the model performance.